What if everything you thought you knew about the universe was just an illusion? From the edge of a cosmic hologram to the idea that gravity itself might be an illusion, the universe is packed with mind-bending concepts that challenge everything we thought we knew about reality. In this stellar story, we'll explore 10 ideas that could rewrite the very laws of physics, each one more astonishing than the last. From time emergent gravity to infinite multiverses, these concepts aren't just wild speculation, they're grounded in cutting-edge research and the best minds in science today. So stay tuned, because the journey into the ultimate frontiers of reality starts now. Number 1. Retrocausality. Most of us think of time as a one-way street. The past shapes the present, and the present shapes the future. But what if the future could also reach back to influence the past? This mind-bending idea is known as retrocausality, and it challenges our everyday understanding of cause and effect. In some interpretations of quantum mechanics, such as the two-state vector formalism, retrocausality suggests that events today can be influenced not just by past causes, but also by future conditions. This isn't science fiction, it's a real possibility within the mathematics of quantum theory. Some experiments, like those involving delayed choice quantum erasers, seem to show that the measurement you make now can affect how particles behaved in the past. It's as if the future is woven into the very fabric of the present moment. If retrocausality is real, it could force us to rethink the arrow of time itself, and maybe even the nature of free will. Do we shape the future, or is the future also shaping us? It's a radical concept that suggests time might be much stranger than we ever imagined, more of a web of interconnections than a one-way river. Number 2. The Holographic Principle. Imagine if the entire universe, every star, every planet, every atom of your body, wasn't truly three-dimensional, that everything we see, feel, and experience is actually a projection from a distant boundary, a cosmic surface where all the real information is stored. This is the holographic principle, the idea that our three-dimensional universe is a hologram of data encoded in just 2 dimensions. It's a mind-bending concept, but it's backed by serious physics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have an entropy, a measure of information, proportional to their surface area, not their volume. This hinted that perhaps the universe itself works the same way. Later, physicist Leonard Susskind extended the idea. All the information in our three-dimensional world could be described by tiny bits written on a 2-dimensional boundary far, far away. This doesn't mean we're living in a simulation. Rather, it's about how information is stored at the deepest level. Think of a computer screen. The pixels are 2-dimensional, but they create a 3-dimensional world of images and videos. In a similar way, the holographic principle suggests our world is an emergent illusion from a more fundamental 2-dimensional cosmic code. What's even more mind-bending is that this idea links gravity, black holes, and quantum physics together. It's one of the leading clues that a true theory of everything might exist, uniting all the forces of nature. Number 3. Loop quantum gravity. If the holographic principle hints that our reality is encoded in 2 dimensions, loop quantum gravity takes aim at the very fabric of space-time itself. In the everyday world, space and time seem smooth and continuous. But what if, at the tiniest possible scale, space and time are woven from tiny, discrete loops? That's the core idea behind loop quantum gravity, or LQG. Instead of treating space as a continuous backdrop, LQG proposes that it's made of minuscule loops of quantum threads. Picture an endless cosmic tapestry, each loop a single thread, collectively weaving the shape of the universe. These loops are unimaginably small, billions of times smaller than the nucleus of an atom. At this Planck scale, the loops combine to form a granular structure, much like the atoms of a crystal. It's a radical break from our intuition, where space and time are not infinite fields, but built from these basic quanta. One of the most compelling features of LQG is that it avoids the infinities that plague other theories of quantum gravity. In a universe woven from loops, black holes might not have singularities at their cores. Instead of a region of infinite density, there might be a bounce, a bridge to a new universe on the other side. Though still a work in progress, loop quantum gravity gives us a tantalizing glimpse into a world where geometry itself is quantized, a place where the building blocks of existence are woven from loops and space is never truly empty. Number 4. Emergent gravity. Gravity is one of the most familiar forces we experience, but what if it isn't a fundamental force at all? That's the radical idea behind emergent gravity. This concept suggests that gravity might actually be a consequence of something deeper, an emergent property arising from the collective behavior of more fundamental building blocks, much like how temperature emerges from the motion of molecules. One of the leading voices in this area is Erik Verlinde, a Dutch theoretical physicist who proposes that gravity might be a manifestation of changes in the information content of space-time itself. In his model, gravity is not a standalone force, but rather a byproduct of entropy, the universe's tendency to move toward disorder. If emergent gravity is right, it could help explain some of the mysteries of our universe, such as the puzzling behavior of galaxies that seems to require dark matter. Verlinde's ideas suggest that what we call dark matter might not be mysterious particles at all, but rather a sign that gravity itself changes in different conditions, emerging differently at large cosmic scales. This is a bold, still controversial proposal, but if it's true, it would fundamentally rewrite our understanding of how gravity works, showing that even the familiar pull of the Earth beneath our feet is just the tip of a deeper iceberg of cosmic information. Number 5, the multiverse. What if our universe is just one of countless others, each with its own version of physics, its own beginning and end? This mind-bending idea is the multiverse, and it suggests that the reality we know is just a single bubble in an endless cosmic ocean. The multiverse concept comes in many flavors. In some theories, it arises from the inflationary burst that launched our universe. In others, it's linked to quantum mechanics, where every possible outcome actually happens in a separate universe. The implications are staggering. If true, it means that everything you know, the laws of physics, the constants of nature, are not universal truths, but local rules of this one bubble. Other universes might have different values of gravity, different particles, or even entirely alien physics. The multiverse might also solve some of the deepest puzzles in science. For example, why do the constants of nature seem so perfectly tuned for life? In an endless multiverse, every possible combination exists somewhere, so it's no surprise we find ourselves in one of the rare universes where life is possible. Of course, the multiverse remains a bold idea. There's no direct evidence for these other universes, and some physicists argue we may never see them. But mathematically, the multiverse pops up again and again, a testament to the profound possibility that our cosmic home is just one small part of a much bigger story. What if the universe isn't a one-time event? Sir Roger Penrose, a brilliant physicist and mathematician, proposed a radical idea called Conformal Cyclic Cosmology, or CCC for short. In this theory, the universe doesn't have a singular beginning and end. Instead, it cycles through endless aeons, each one starting with a big bang and ending in a smooth, cold expansion. The key idea is that when the universe becomes infinitely stretched out and empty, time and distance lose their meaning. At that point, the end of one universe can be mathematically mapped onto the beginning of a new one. It's a breathtaking vision, an eternal succession of universes, each giving birth to the next in an endless cosmic cycle. If true, it would mean that the universe we see today was born from the death of a previous cosmos, like a phoenix rising from its ashes. There's even a tantalizing hint in the data. Penrose and some collaborators have claimed to find faint circular patterns in the cosmic microwave background radiation, potential echoes from a universe that came before. Though CCC remains a bold and speculative idea, it challenges us to see the universe not as a fleeting fireworks show, but as an eternal dance, where every ending is also a beginning. Gravity, the force that binds the stars, that tethers us to the Earth. But what if gravity isn't actually a fundamental force? That's the mind-bending idea behind entropic gravity, proposed by theoretical physicist Eric Verlinde. In this framework, gravity emerges from the collective behavior of microscopic building blocks of space-time itself, like an emergent property of a complex system. Just as temperature and pressure aren't fundamental forces, but arise from countless moving particles, gravity, too, might be a byproduct of the universe's information, content, and entropy. In simple terms, Verlinde suggests that the pull we feel as gravity is really a statistical effect, like nature's drive toward disorder manifesting itself on a cosmic scale. The implications: it could explain dark matter and dark energy not as separate, mysterious substances, but as consequences of the way information is woven into the fabric of reality. Instead of seeing gravity as a primary actor, we might understand it as a side effect of the universe's most basic ingredient, entropy. Though controversial and still debated, entropic gravity challenges us to see gravity in a new light, not as an inescapable law of nature, but as a shadow cast by the deeper workings of the quantum world. Number 8, quantum Darwinism. Let's journey deeper into the quantum fog with a concept that might explain why we see a clear classical world instead of a constant quantum blur, quantum Darwinism. This idea, proposed by physicist Wojciech Zurek, suggests that classical reality emerges from the quantum world through a process not unlike natural selection. Just as in biology, where only the fittest traits survive, in quantum Darwinism, only the most robust, redundant quantum information persists and becomes part of our shared classical world. Imagine that every object is constantly interacting with its environment, like a tree in a forest of whispering winds. Each interaction spreads bits of quantum information outward, and some of those bits, like echoes of the object's existence, are stronger, more repeated, and more stable. These robust echoes survive the quantum chaos, giving us the stable, classical world we see around us. It's a poetic picture, the quantum jungle teeming with endless possibilities, but the strongest patterns, the fittest, are what we actually observe. Quantum Darwinism doesn't just explain why reality looks classical. It's a window into how information shapes the very structure of existence. Number 9. Variable speed of light. For most of us, the speed of light is an unchanging cosmic speed limit, about 299,792 kilometers per second, woven into the very fabric of reality. But what if it's not a constant after all? Enter the cutting-edge idea of a variable speed of light. This theory suggests that light may have traveled faster or slower in the past, or in different conditions. If true, this would overturn one of the bedrock principles of modern physics, Einstein's theory of relativity, which assumes that the speed of light is constant for all observers, everywhere and always. Some cosmologists have proposed this idea as a way to solve mysteries in the early universe. For example, in the moments after the Big Bang, the universe seems to have smoothed itself out faster than the laws of physics seem to allow. If light was once faster, it might have zipped across vast distances in those first moments, ironing out cosmic wrinkles and creating the smooth, uniform cosmos we see today. But it doesn't stop there. A variable speed of light would have deep implications for our understanding of causality, information, and even the age of the universe. It's a wild idea that challenges our assumptions and hints that the laws of nature themselves might be more flexible than we've ever dared to imagine. Number 10. Superdeterminism. At the cutting edge of quantum physics lies a puzzle that has fascinated and frustrated physicists for decades. The question of whether reality is truly random or if everything is, in some deep sense, preordained. This is where the mind-bending concept of superdeterminism steps in. Superdeterminism suggests that what appears to be random in quantum mechanics might not be random at all. In fact, it proposes that everything, every particle interaction, every experiment we run, even our own choices, are predetermined by the initial conditions of the universe. In this picture, the free will of the experimenter vanishes. Even our decisions to measure or observe something are already encoded in the universe's starting state. This would be a dramatic challenge to the standard view of quantum mechanics, which holds that particles can exist in multiple states until they're measured, and that the outcomes of measurements are fundamentally probabilistic. If superdeterminism is correct, there's no real chance at all, no dice being rolled by the universe. Every outcome, even those we think of as random, would be the inevitable consequence of initial cosmic conditions. This idea is still controversial and speculative, but it forces us to rethink one of the deepest questions. Do we live in a universe of true randomness? Or is everything, including your choice to watch this video, already written in the cosmic script? The universe is stranger, grander, and more mysterious than we could ever imagine. From the mind-bending holographic principle to the dizzying possibility of superdeterminism, these 10 concepts challenge everything we thought we knew. We're only beginning to scratch the surface of these mysteries, and who knows what secrets await as we continue to push the boundaries of human knowledge. If you've enjoyed this journey through the most mind-bending ideas in physics, please like this video, subscribe to Stellar Stories, and join us as we continue to explore the deepest questions of existence. Your support helps this small channel keep growing and creating new cosmic stories. Thanks for watching. See you next time.